Our next talk is Fetal Developing Human Connectome Project, Functional MRI Data Release, Methods and Data Structures. And that's from Vyacheslav Karolis at King's College London in the Department of Biomedical Engineering. Thank you, Vyacheslav. And all yours.
No.
Right, don't forget, if you want to still ask questions from previous speakers, to go on the app, and we can maybe, if we have time at the end of the session, we will accommodate for those questions.
Okay, this is correct, yeah. So I'm going to talk about developing Human Connectome Project Fetal Functional MRI Release dataset. So, oops. Doesn't seem to work. What? Ah, this one? Okay, sorry. And I have no disclosures. Okay, let me start with giving you a bird's eye view on the field of in utero functional MRI. So first of all, it's an emerging field of research, quite new, and the more and more papers are published. But it's obviously a very challenging data type, very difficult to acquire and process. We inevitably deal with a very low signal-to-noise ratio in this data due to various factors, including greater distance between head and coil compared to ex utero data. We also signal can be contaminated by high contrast non-rigid maternal tissues, leading to a leakage artifact and difficulty of fat suppression. And most importantly, motion-free periods are basically non-existent in this data. So we're leading to inconsistent sampling of anatomy, spin history, effects, dynamically evolving geometric distortions. And whereas in ex utero data, we're talking about reproducibility and harmonization. We're just in the beginning of this road in utero. We are yet to set standards for acquisition data processing. And I guess it requires community-wide effort to deal with these things, and obviously availability of open access data could help in this direction. So the HTTP fetal cohort release basically tries to make the first step in this direction. So we released the first open access fetal neuroimaging data, which includes various modalities, including resting state of MRI. We implemented a systematic bottom-up approach to data acquisition and processing, starting from the very first steps to the levels of group-level data fusion. And we release outputs from the main preprocessing stage, from the main preprocessing stages, so our data can be used as a template for future method development and method benchmarking. So in order to acquire data in this high motion regime, you need to really implement fast acquisition sequences. That's why we use single shot field echo sequence and used multi-band acceleration. However, there is certain constraints on how quick you can do this. Particularly, T2 star is longer in an immature brain, and which means you would perhaps need a longer echo times to implement, and as well, the longer echo time helps to suppress fat in this data, fat signal in this data. Your special corrections needs particular treatment as well, because inconsistent sampling of brain anatomy almost necessitates slice to volume reconstruction, and it can be demonstrated that actually it's outperforming standard volume to volume alignment typically used in ex utero data. It's also required modeling binode field and homogeneity in order to implement dynamic distortion corrections. In our case, we use face images to deal with this. But even after spatial correction, you are left with a significant amount of temporal artifact in the temporal domain. And so what we try to implement is a regression-based model which regressors try to address dominant sources of artifacts in this data. So it starts with the artifact low frequency temporal drift and signal intensity, for which we use low-pass filtering using columns of discrete cosine transform matrix. Inevitably, there will be poor motion correction at the period of extremely high motion. It's almost necessary. It's volume censoring, which was implemented by spike regressors. We still may have potential leakage artifacts which were not fully suppressed during reconstruction. And to deal with this, we introduce a new type of regressor, voxel-wise regressor, which we called folding maps. Essentially, what it means is when you acquire data in multi-band sequence, for each voxel in the brain tissue, you got two companions, and you use time series of these companions to account for potential leakage, remaining leakages. And so basically you fold this time series into the brain tissues. Again, another new type of voxel-wire regressor is the density maps, which tries to address potential residual effects of dynamic distortion corrections. And essentially it's an evolution of Jacobian modulator over time, which apply to the data to compress and stretch the data in phase coding dimension. And there will be also residual motion related and physiological artifacts, for which we use a rich set of motion parameter maps and also include quadratic and differential terms, as well as data-derived regressors. The problem is how to apply a model which is optimal, because the conceptual problem here is that we don't have a ground truth for what is the best model. And if we are going to be too conservative and apply too sophisticated model, we may inadvertently remove signal which in the settings of fetal fMRI is quite undesired. We already operate at a very low signal-to-noise ratio regimes. So the approach we took to our data is to implement what we call signal implanting test. The idea here, so we inject biologically plausible signal taken from neonatal data into the fetal time series, scaled appropriately, and then we try to apply models to see which candidate model can outperform other ones with respect to signal recovery and signal loss. So essentially, it also implies that optimization is done with respect to accuracy of estimating whole brain cortical connectivity. So the application of this test is facilitated by the fact that our fMRI data is integrated in the HTTP registration pipeline, which allows flexible mapping between various spaces, including neonatal template space. So in order to simplify model testing, we define a set of baseline regressors, which we used in all models simply because they seem to be useful irrespectively. And we test a set of models which span from models which enrich with motion-based parameters without no data-derived regressors to the greedy models which combines both motion-based parameters and data-derived regressors to the models which are enriched with data-derived regressors but without motion-based regressors. And the resulting best-performing model it turned out to be enriched with motion-based parameters and a small set of data-derived regressors. It outperforms other models with respect to signal recovery, but which is on the left here, where the bigger number is the better. And also it's preserving signal loss, which is shown on the right, where a smaller value is better. You also perhaps can appreciate at the bottom that after denoising, we have a significant reduction of spin history effects, which are evident here on the left as a traveling, non-stationary traveling waves, which are quite difficult to tackle in the fMRI data. So eventually we come up with 263 fully preprocessed data out of original 275. The quality assessment is a special topic, which is difficult actually to discuss at the moment because, again, there is no norms how to estimate quality here. So we use combination of various complementary metrics, including visual assessment. And we, based on criteria, predetermined criteria, we come up with 270 cases which we think could be suitable for the analysis. Okay, so this is summary of preprocessing stages outputs and also data types released. So we start from sensors abstraction, then we follow to dynamic distortion directions, then we do slice to volume construction and temporal filtering. So the data structure follows the format of bits. Even so, in reality, the data types which we have here is not really fitting the current bit standards. But we try to follow these recommendations so improve usability of the data by that data users. And for those who are interested in details, there is a preprint, recent preprint on the methods, detailed preprint, as well as a critical evaluation of what we did and short comments of our approach. I really hope that this data set can be useful for neuroscientific community, because in addition to fMRI data, it includes anatomical data, diffusion data, as well as complementary non-imaging data. So you may find also useful the GNode repository, which contains the HCP special temporal atlases, both volumetric and surface. And I'm going to be at the poster to 2219 tomorrow. Thank you.
Thank you. And while we switch speakers, maybe there's one quick question from the room, which is how strong are the B1 homogeneity artifacts in the fetal brain MRI dataset? Do you have a lot of B1 homogeneity artifacts?
B1?
B1, yeah.
Oh, sorry, I'm not an expert, to be honest, on the physics. So, I mean, if you're interested, I can point you to the right direction. I'm not sure about B1, to be honest. Maybe okay. someone.
So. No? Redirect you to your poster.
Yeah, so I mean, we can come up. We got a team more experienced in this, and someone knocks that actually it's not.
Thank you again.